Hello, Calc 1. Here we are in our second video. I guess if school started Tuesday, we met Wednesday, Thursday. We should be viewing this Thursday after class at some point. And we're going to talk about some properties of limits today. So you can title your page Properties of Limits, and we're actually backtracking and using some principles that I've already, or establishing some principles I've already asked you to use on your classwork. So I think I mentioned this. I really should establish some things and tell you some things, but go ahead and do it anyway. So here we are. We're going to be very rigorous this year in that anything that we use we have to establish first, logically. So let's go back and establish some things we've actually already used, and I think you might recognize them as we establish them. Well, these are going to be theorems, and we're going to start with B and C as an element of the reals. They're constants, and is an element of that little symbol, and n is a positive integer. So the first one, and I'll be going quickly so you can stop the video to catch up if you need to. The limit as x approaches c of b equals. See if you can fill in what you think that limit is. It turns out that this expression, just b, is a constant. It has no variable x in it, for x cannot approach c when there's no x in the expression. So b is unaltered by this limit, so it's just b. So hopefully your intuition took you there before I did. The limit as x approaches c of x. Now we have a variable x in our expression that x can approach. We're going to use substitution, and we'll see that x takes on c. That's the limit. Never really gets there, but it approaches it. The limit as x approaches c is x to the n. C will go in for x, and you get c to the n. The next section, we add some new players on our game. F and G are functions, and it could be any function. We've studied tons and observed tons of functions, like y equals x squared, y equals the square root of x plus 4, etc., etc. So F and G are functions, and we know the limit as x approaches c of these two functions. F goes to L and G goes to K. So we have some definitions here, some truths established for this section. So, what would be the limit as x approaches c of b, remember, is a constant, times a function, f of x? It turns out that as x approaches c, we will substitute the variable with the constant c, so we will evaluate this function at c. So everywhere there's an x, we're going to plug in a c, and the b will come along for the ride. But are we finished here? No. So f of c, we already know that this function, as x approaches c, this function goes to L. So we can jump and change f of c to L. So we have b times L. Alright. Now, this function is going to, these two functions are going to be added. The limit is taken as x approaches c. We know up here that f of x approaches c, we get L, and g, we get k. So all we have to find out is that as this goes to c, we get an L, and as this goes to c, we get a k. You may hear me say this in this way: the limit of the sum is the sum of the limits. So that's a way that I might remind you about that principle. Same for multiplication down here. When you multiply two functions and you know the limit of each, the limit of their product is going to be the product of their limits, L times K. So if we were going to look at this one, this would be, this would take, I would call this one the constant rule. This one, I would say it's the addition rule. And this one, I would say is the multiplication rule. So, you can see that obviously. Alright, these will go on over here. Let's see if I can move the board, then we'll come back and do a couple examples, and I'll check the time. All right. So over here, we have the limit as you probably could foresee, and now we're going to do the division rule. It's going to be dividing. So if we have the same parameters, sorry, it's just a meter stick. I'm in the lab, I don't have much room to move around here. The limit as x approaches c of f of x, we've already established that that limit is L, and g over g of x, we've established that limit is k. So therefore, it's going to be L over k. The way I might say it in the future is the limit of a quotient is the quotient of the limits. And lastly, we have a power going on. And the limit as x approaches c of f of x to the n. We already know the limit of f of x, and that was L. So we just we're going to raise L to the n. And that will be how the products work. So let's go ahead and look at some examples, and you'll see why we use how we use these things in our everyday problems, and have already done that without the rigorous foundation, but now I came back and slipped it under your feet. All right, for example, what is the limit as x approaches 2 of 3? Can you find a principle that we have discussed that will allow that to be done? I think so. This is following the first one, and you can see that there's no x in the expression at all for x to change to a 2 or approach 2. So therefore 3 will be unaltered by this limit, so you just get a 3. It follows principle number 1. How about the limit as x approaches -4 of x? So the limit as x approaches -4 of x equals. Well, now we have an expression in the problem, so as x approaches -4, we just plug in a -4 for the variable, and we do get -4. And another one, you can see I'm going down the list here. The limit as x approaches 2 of x squared. Fill in what you think it is. The limit as x approaches 2 of x squared. Plug in a 2, square it, and we get 4. Alright, so actually you have been doing this. When I taught you the substitution, you were actually doing this in the assignment. And again, the rigor is there for you to continue doing it. Let's go ahead and look at some examples from down here. Not every single one to show up. I forget where I am on the board. The limit as x approaches 2 of 4x squared plus 3. Alright, so here we see, if I'm going to rigorously understand how we are able to do this one, I have to split it up. So I'm going to split it up into the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3. So notice I use the addition rule in order to do that step. So now I'm going to use the rule. I'm going to take this 4 and I'll move it across the limit, and tell me why I could take that 4 right on out of the limit problem. Let me get out of your way here. Why could I move this 4 right across the limit? Let's see if that's showing up. That low? Yeah, I'm just about out of view. I think I can finish it. So the reason I can take this 4 across the limit is because of principle number 1. The limit is not affecting that constant at all. It has no x in it. So I'm pulling it across, and now I'm going to use the power rule, which is over here. I'm not sure if they're all showing up at the same time. That's why I named them. So number 8, the power rule. So putting that all together, I'm going to get 4 times, when I get to here, I'm going to sub in the 2. And the limit of 2, limit as x approaches 2 is 3. Since there's no variable in there, it doesn't change. So I get 4 times 2 squared, 4 times 4, 16 plus 3. And I don't think you have a very good view. Let me check and see. Oh, I think it might have shown up. All right. So I'm going to shut down this portion of the video. Oh, no, I'm not. I have 2 more up here with blanks. So let's fill those in, and then I'll shut down that portion of the video. All right, on number 9. So this is why, of course, when you look at this in your homework, you're just going to plug a 2 in and chug it out. But I am now explaining to you step by step, inch by inch, why you can do that. So, all right. Over here, functionally, you'll do them just like you have always done them. All right, the limit as x, now we're going to add 2 more players. P and Q are polynomials. Do you remember what a polynomial is? All right, that is, for example, a polynomial could be like P of x equals 3x to the 5th plus 2x to the 4th minus 3x cubed plus 2x minus 5. So we worked with polynomials off and on throughout. And this polynomial is a polynomial because the coefficients on each term are real numbers, so we can't sneak in any imaginaries on our polynomials. And these numbers, the exponents, have to be integers which are not negative, non-negative integers. So they can't be like 3/2 for our exponents. So that's the rules of a polynomial. So just a review for that. Let's get that out of the way. It's kind of cluttering our view. All right. The limit as this polynomial P of x as x approaches c is simply found by putting x into the polynomial and evaluating it at c. And I'll indicate that by P of c. And the last, the limit of a polynomial divided by another polynomial, that's a rational function, you will see is going to be P at c over Q at c. Alright, so those are, and whenever I divide, I should be even more rigorous, and I need to tell you that the denominator cannot be 0. Where else did that happen? Up here, I should have said k cannot be 0. So, whenever you have a denominator, we're assuming that. So, let's do an example from this, see if I can squeeze one on, reaching over the table and all the junk in here. Let's do the limit of x squared plus x plus 2 over x plus 1 as x approaches 1. So here we have a rational expression, a polynomial in the num, a polynomial in the denom. So all we're going to do, according to this rule, is substitute. So we're allowed to do that. The limit as x approaches 1. These expressions, just put in a 1 squared plus 1 plus 2 over 1 plus 1. So that gives us a 4 over 2, which is 2. Alright, so I have a few more to give you, but I will put those on I'm going to clear the board and put those on the next video. See you in a few.